the goal is to show you that adding a process to EAMxx is pretty simple and it's relatively painless. And you can do it in one sitting, in an hour, one afternoon. So that's the goal. And for this process that we're showing you, what we thought would be good to show you is a volcano. The acronym, Luca came up with the acronym POMPEI, and that's why there's one I in it, not two, because in Italian it's one I. So credit goes to him, and Aaron did all the graphics in this. So if you like them, that's what you think. Let me stop the presentation because I want to show you the code. And I have two versions for you. If you want to follow along, which you should, you have two ways to do so. One is I'll be adding new code to a fresh branch, but I also have done everything that I will be doing today this morning, and it is in this branch tutorial material. So you can jump ahead and run stuff in this. It will have everything that I'll be going through. And I'll be pushing changes right now to this branch once I start. So I'll show you what we have here. This is all the code we need. We'll have coded by the end. It's not much. Hopefully you agree. Okay, so back to the presentation. Let me make it this way. Again, the goal is to add a new process, and we'll see how that goes. Adding a new process in EAMxx has essentially you need to add some code that does something, but what EAMxx wants from you is you want to connect that code to EAMxx through an interface. And we'll go through what this interface has and what it expects you to add. There are very specific things that you need to override in order for it to work. And then you need to add the new process to CMake so that it's exposed, the MCT coupling layer. And then also you have, if you want, you can add runtime options. So this is what we'll be doing today, basically. So in other words, what we're going to do, we're going to have code that injects some ash into the atmosphere. We'll couple that to EAMxx through an interface layer. And this interface has 4 components that we'll code. And then you can run EAMxx and you'll have a volcano in it that's active. Any questions so far, or we're good? It's kind of clear what we're trying to get done. Okay, so in order to get started, this is going to be less me talking, more you coding. So in order to get started, I hope everyone joins. In your E3SM repo, you would want to go to the physics directory, so the EAMxx source physics directory, and you would want to make a new directory called POMPEI. And I'll be also doing this with you, and I'll be pushing, basically, I'll try to stop every slide or every step and push code so that it is there for if people want to copy what I pushed. So what I'll be doing, I can also just copy exactly this. It should work. You should also have the slides somewhere.
I want to make the journal
Bigger, okay. Yeah. Didn't I get bigger? They did not.
That's like
Command plus.
plus.
That's what. Yeah. Or maybe I'm on my older branch, so I'll go back and start over so that.
So we're putting the interface templates in the physics directory, not the POMPEI directory, or the POMPEI directory?
The POMPEI directory.
Ah, okay.
So I'll try to keep this screen active, both of them at the same time. So if you cd into this directory and then do mcdir, and then cd to POMPEI. So I am in this directory right now. So what you want, we have put the templates on CFS, so you should copy them inside POMPEI. And then we want to change their names quickly.
Is this something you're doing just is this simply good programming practice, or does EAMxx or this directory name?
No, you can change the directory name. Yeah. This is just to like keep us on the same page. Yeah, that's the goal.
And I would add that I think it's helpful to know that most of the EAMxx physics code follows what we're
Yeah.
doing here. So if you're familiar with these steps, then it makes it clearer.
Yes. So P3, shock, TMS, other parameterizations follow these conventions. And we try to kind of make them as similar as possible so that the code doesn't look foreign to you. So once you add these, we'll move on to the next step. So the other thing in this, so we have a skeleton for this process, and it only calculates the emission rate. And so you should just copy these files and add them to your POMPEI directory as well. So let me look if I have them now. I have everything, which is good. And in these files, you will see essentially you just calculating the emission rate. And I can explain them more if needed, but maybe we can do that later. But if you copy the files, you'll have the content of these two files in your directory.
Maybe just to help for people who are unfamiliar with C++. We kept them as simple as possible, just so you can kind of see what a very basic process would look like. And if you had a more complex process, you would very likely have some things like your file, CPP file.
I'll just open one of them for, that's what the header file has. It just defines the function, not just sets, its signature definition, and then the actual definition of the function is in the CPP file. And it only does, basically, there is an emission rate that you calculate based on a decay rate and an initial emission as well. So, but these details, you should feel free to add them if you want. But this is just a very simple example to get you started. And if you do have questions about, what this C++ code means, please ask. We can explain it in more details, but it shouldn't be hard to read, hopefully. So this concludes the skeleton part where we just add the skeleton of the code, and now we're starting editing the code. And especially important are, we need to edit the interface. So the interface in EAMxx, it's an instance of an object that's called atmosphere process. And at a minimum, EAMxx expects you to override, that means to have an implementation of, in your code, of these four methods: set grids, initialize impl, run impl, and finalize impl. So you have to override these in your interface files. And we'll go through what we will do in every single one of these one by one slowly. And we also want you to have a header file and a source file. So HPP is the header file, and then the source file is the CPP file. So we'll start with the header file because it's much simpler. in the header file that you have, which will be EAMxx POMPEI process interface.hpp, you want to change any instance of AP template to uppercase POMPEI. So you should do that. If you have a fancier editor, you can do that more quickly, but it's often, huh? Yeah. Some people believe that Vim is a proper text editor, so you believe that you can try to edit stuff there. But what's important here is that so once you change AP template to POMPEI, all uppercase, I'll also change the comments just to be consistent. You can look at this file and you can see we're including a header file from the atmosphere process. So this what gives you access to this atmosphere process that we're inheriting from. So POMPEI is an instant of atmosphere process. And then inside of it, the first item is a constructor. I didn't change that one, so I'll change it now. So in the constructor takes a communicator, and params as arguments. And then we also want to change the name to something meaningful. So I'll just call it POMPEI, or POMPEI eruption, but just POMPEI for now. Go ahead.
Just really quick, so the little code is just the ACE copy there. That was very generic C++.
Yeah.
But down here is very EAMxx specific.
Yes. Yeah. And these are the things that you have to edit at a minimum. So these are the 4 methods that you write, Luca, or no?
5, 6, 7. Oh, it's
What is constructor?
constructor path, type, and name also must be.
Yeah.
But those are the one-liners. But yeah, there's like, if you look at the base class, is like quite big, and there's like many more that you could override to get like fine-grained behaviors, but those are not required. There's some default implementation that will work for our case. But these ones, there's no implementation in the base class, so you are forced to define them. And the constructor, it is true that you can construct the class in whichever way you want, but EAMxx uses a factory-based design to build processes, and it assumes that your instance is constructible from a communicator from the ECAP namespace and ECAP parameter list. So if you don't have that constructor, the factory machinery will have a compilation. You can have 2 or 3 more constructors, but they will not be used by EAMxx.
And so the next step is also we need these 4. So the methods are already there for you, but the variables I just added at the bottom, these 4, util timestamp, eruption start, and then a shared pointer to grid, calls and nlevs, as well as emission mask. These are things that you want to add. And the prefix m_ is for member. So these are member of a class. And these will be visible throughout all methods in the source code once we get to it. So you want to add these 4, and this will be the end of what we're going to be doing in this file. Any questions? I wouldn't worry about the meaning of what these types are for now. You just know that that's the required type for them. The timestamp, the short pointer of an abstract grid, etc. Don't overthink it. It's not that important.
And maybe we're pointing out that when you write your own process, you may not need these. Maybe you need something else.
Yes.
Now implementation, we end up needing
Just these. Yeah.
these objects, so we store them in it.
Yes. And part of the exercises later will be potentially we'll add to these if you want to do fancier calculations. So this will be in the header file. Anything else? Any questions about the header file or any comments?
Do folks understand what we mean when we say inheriting? You know, that a lot of us aren't as familiar with C++ as we are fortunate.
think the important is called extends.
Go ahead. Sure. Yeah.
C++ is case sensitive.
And that's actually a good question because you will see we'll use lowercase for something else in a second. Go
Or
ahead.
you could name your, I don't know if this is part of the question, POMPEI doesn't have to be all upper.
Oh, yeah.
Right. You're free to choose lowercase, but you cannot mix and match. Once you use a name, stick with that. The string here in the method name, that string inside is just something that gets printed to the screen. But it's not a variable itself. So that can be whatever you want. But the name of the class, once you choose one case, it has to be that.
I can't find that slide, it's like that.
Yeah, can I just, I was gonna say, I downloaded the slide from
Oh, so
the
there's
Slack channel that Conrad pointed to 4 hours ago, and they're not.
different. Okay, so maybe Conrad
Version or?
Yeah, so I'll upload the version of record right now. Sorry.
Two presentations be uploaded.
No, but you can probably upload it. You want to have the actual implementation under to be not trying to pull variables to be all sort of constants and things like that. Like the idea is we want to be able to have everything tasks signature for
Yeah.
unless it's a constant.
Yep.
So trying to keep it.
Yeah, and that's so the set. Those are the methods that we're going to be overriding now. We'll expand on what Peter is saying. So now we go to the source file, the CPP file, and you should have. This is going to be a little bit involved, so it's going to be a bit of work to get this to the place where you need it to be. But this is a big file, and the first thing to do is you want to change AP template to POMPEI again, the same way you did in the header file. So make sure if you chose a different case, etc., ensure that you have it the same way here. And again, so what you do in the header file is you define the signatures, and in the source code, in the CPP file, you define things, and you potentially edit them and manipulate them for what you need. So the first one is the constructor. So before this, I will just say again, the tasks here, we have 5 different things we need to override and manipulate in this file. And we'll go, because they are a little bit more involved, we'll go through them one by one slowly. So first, actually headers, I didn't think about yet, but so we need headers to get some utilities we're using throughout the code. So the first header is the header that we just edited, so include that. If you don't want to type things and be at the mercy of typos, you can copy from my branches, but I'm gonna be typing them just because it helps to get muscle memory with this stuff, in my opinion, at least. So the first one, we'll give the header for the interface we just defined, and we will do, we want to have access to physics constants. So this is actually a question that came up earlier, where we were talking about physics constants. So we're including these physics constants because we're gonna have access to them.
This is in the brief that.
Yeah, in the EAMxx POMPEI process interface.cpp. Yeah. And then the last one we want to include is the process file, which we included the emission rate function in. Let me know if you have questions. Sorry?
Which one? You'll make sure you
I just did the headers, the includes. Yeah. I'll get out of this. I'm in the CPP file.
in the header, interface header file, switched a template to POMPEI, and added those 4 lines to the second section.
And I changed the name, and that's it.
Changed.
Yeah.
Down here,
The first step is to add the headers that we need, and then we'll go through one step at a time because they're a little involved.
Adding the headers is very similar to incorporating modules, right? So you don't, this code doesn't know about any of the stuff we do without being able to look at the header. So essentially pointing to the header files that are necessary.
Yeah. And forget to include one, you'll know.
Yeah, you'll get an error later. So if you're done with the headers or the includes, we can move on to the constructor. Oh, sorry. Yeah, go ahead.
Why the second include is specify the physics shared? What if we don't specify that?
So
Maybe
by default, C++, if you don't specify any path, it looks in the current path or in any other path that the compiler already knows about.
Current path is the current field directory.
No, in the current path where this file is located.
Well,
So in this case, the header and the CPP are in the same path, so you don't need to specify the path.
oh, okay. So the first one,
The first one by default, it looks in the folder where this file is located, and I find interface.hp. Yes, great. The other one is in a different folder, and
This is
you don't need to specify the absolute path, but the folder physics happens to be in EAMxx/source, which is itself added to the include directories of the compilers.
in the key thing to be should say, when compile this file, so without specifying, directly forget that. Yeah.
Yeah.
The current one is
The current one is always inserted by the current of this file, not where you're running the mouse.
But then what will be the top hat for the physics?
Physics happens to be, as I say, like the folder where physics is inside EAMxx/source, which we already tell the compiler to look at, because most of our files are inside EAMxx/source, and so we just need to specify a relative path to that folder.
Oh, the source is already.
We already take care of telling the compiler to look in there. Yeah.
But there is no more fair share folder of the physics.
source.
EAMxx/source/physics
Source
there.
the one of the include path.
Yeah, so we're being like as specific as we need to be without more specific. So you could put in source, all of the whole path under one, could you?
I don't know if source will work, because I'm not for that EAMxx as a search. Anyway, that's a compilation. I think we're getting lost in that.
So this file, do you want me to open this file to show people what we have in it quickly? Yeah. So you can, if you are on GitHub, you can do T and then what is the file called again? Physics constants. So this is what's in this file. All sorts of constants and things that are not supposed to change. And I'm including the constants because I'm going to use gravity at some point, just as an exercise. Not that it matters, but just make it thing slightly better. Okay, so the constructor. The constructor is where you instantiate an instant of the atmosphere process object. And we usually don't really do much in the constructor except getting the like the name list parameters, the parameter list. You can do other things there if you want, but we usually don't really do much in it. Just so you know. But we will go ahead and do the start time. And it's a runtime. We're going to make it a runtime parameter later. So we will get it here. And recall that we defined that eruption start in the header, so we can access it without having to declare it. And we do here we're using a little utility to convert a string to a timestamp, but that's a detail. By the way, is my font big enough or no?
Yeah.
Okay.
What does it mean to you that your variables start with M underscore? What is M?
Member of the class. Is that right?
So when you read the code, you know if the variable is a local variable or is a class member. There's different styles that who just adds an underscore at the beginning. There's people that add uppercase and just. Okay, we went with that. It's like, as long as you're consistent and at least inside of parameterization, it's
And you will see there are some comments. I think Luca and Aaron added the comments. They're very helpful. So if you think I'm saying something stupid, the comments should be there to help you.
function name is timestamp without underscore. No underscore between timestamp.
There is underscore.
There is.
Yeah. I ran into it earlier this month. Yeah, that's fine. And also I ran into it because I wrote something else, but there is, I think, an underscore. But if there's a bug, we'll be able to tell once we start compiling. So, okay, if you're.
Just one second, just to explain the template thing.
Sure, yeah.
Together. Just for note, this is the first time we've actually created a template for this tutorial. So this is just created for the tutorial. And that's why there's lots of comments and stuff in it. And the hope is that if it's something that's comfortable, that you can use this in your future development. But this is also a completely new way for us to communicate how you would add an interface. And there are conventions that we've put in there for the purposes of the tutorial, but you'll see as we have this conversation, like the M underscore. And that's the style we're using, but there are some things that you know.
And just, I want to make something very clear quickly. If you go to the HTTP file, you should be able to find that we have defined this as a timestamp. So this is the thing that we're defining right now. So here, you're just declaring it with a type, and in the source file, you're actually giving it a value. And we'll do that for everything on this list, not just that.
So the higher level modules that you're calling, one of them is called ECAT, EKAT. What is that?
ECAT is E3SM, Cocos.
Application toolkit.
It's basically the things that involve a bit of work to make them work behind the scenes, and we don't want users to worry about them.
But just a bunch of utilities.
Yeah.
Okay. There's some focus utilities, but then it evolved into having like a parser for a YAML file
Yeah.
into a parameter list. Some other string utilities. You name it.
In most cases, you will be able to do all of this without, like if you want, without ECAT utilities, but these will make your life much easier. They're just there for ease. So, any other questions about the constructor? So one note is the params list. So when we do the get method on the params, it takes a type, the T there in the end of the slide. And that T, the type can be an integer, a string, a pool, double, or a vector, but nothing else. So this should limit you to what you can define in the name list and the runtime options. But just a note, in case you are thinking ahead about having some very fancy runtime option, these are the only types that you can work with.
And maybe there's string to timestamp is just a utility. The string is expected to be in the format year dash month dash day dash 5 digits for time day.
And then
Very standard string representation. And timestamp is just a struct somewhere in EAMxx that stores a bunch of these.
okay, so if we're done with the constructor, we can move to set grids. Set grids is where we declare the variables that we need in this process and the grid information. So how they are stored in terms of data. So their layout, what their names are, things like that. So this is where we declare everything about, the grid, the variables we have in this process. Everything has to be done here. And I want to define just in words a few things. So you may hear or you may read in the file, there's grids manager, and then there is the concept of a field manager, and then there are fields. So a field manager is essentially stores fields. It's like, a structure that has fields in it, but it doesn't have data. So the field manager is something that lives on the CPU only. It has pointers to where the data is, and it has information about the data. So the names of these variables, their geometry, so their layout, and other information, like their units, for example, all of that is stored in the fields manager. And we call the field manager, we call it FM for short. So the idea is we declare these fields, and then I'll get to the last item in a second, which is we call them, we declare how they behave inside this process by calling a method called addField or addTracer to define how they should behave inside the process. Okay, so in order to edit the template for set grids, you want to remember to change the template to POMPEI again. And then mgrid is just you're getting the grid information. This almost always will not change, especially if you're only working in the physics realm. It will just be physics and you don't have to think about it. But if you ever work in the dynamics, it would be different, or in IOP potentially. And then I'm just going to skip after the comment to add more other things to this file. And the things we need to add are so from the, by the way, this is wrong. This shouldn't be auto. So I'll just comment it out. So comment out that auto mgrid. Yeah, that will give you a bad. Yeah. So it should be mgrid and then grids manager. And if you're wondering where this lowercase grids manager came from, it came from the parent setup. So I wouldn't overthink it.
It's in the function inputs.
Yeah.
That's coming from the atmosphere, the driver.
So again, what we're going to be doing here, as we did with the start time, we'll do the same thing with mgrid. So we're defining the members. So mgrid is just from the grids manager, you get the physics grid. That will be your mgrid. And then the other things I want to do, and I'll try to zoom this in so that I can also see it. You want to define the integer of m calls and then m levels. The little arrow here is essentially you get to call a method from that construct. I don't know, maybe Luca has a better definition.
Reference the point of accesses.
So depending on the structure of the variable you press, you would need to use the arrow versus the null function. It depends on how it's defined. So it turns out that what's returned from the grids manager grid call requires you to use the arrow syntax in order to reference or to get the function.
And it is a shared pointer. So if you're wondering what that object is, it's a shared pointer. So mgrid is a shared pointer, and that's why we're using an arrow. But these are details that you'll figure out as you go. It's not, I wouldn't overthink these little details. So we'll define mgrid, mcalls, levels, and then as more housekeeping, we will include some units because we will need them in the addField, addTracer calls. So I will do const expression, auto, pressure, Pascal. And kilogram for, so pressure, we need the pressure for pseudo density, and we need Thank you. Hopefully I didn't offend Luca, but no, I'm just kidding. So you can also, there are other units. We have all base units defined in EAMxx in ECAD. So you can, if you need more of them, they'll be there. And they work with, you can do operations on them. But again, these are just details that I wouldn't worry too much about them. We don't need the non-dimensional one, so I'm not gonna bother bringing it. And we want to get information about the data layout. So const auto layout 3D. Layout 3D is basically column level. That's what we call 3D. And then we call this again by using mgrid, little arrow, and then get 3D scalar layout, and then true. What is the true for?
So if you say true, is that the quantity is defined at midpoints in the vertical layers. If it's false, it's defined at interfaces.
What's the default? True, I think.
There's no default.
You have to call it now. Okay.
We could probably switch to an enum, be more verbose.
Yeah. So I'm going to call 3D and 2D just to kind of give you an idea how they look. But at first, in the initial swipe, we'll only use 3D because I'm only going to define the bare minimum. But if you want to define something like a reduced quantity, you would want to use the 2D field.
Why is set grids dealing?
What?
Why is set grids dealing with units?
Because the fields in the field manager we design them such that they have information about units.
Fields and grids are the same thing.
Sorry?
Fields and grids are the same thing.
No. Fields are.
So this is the function where you tell the driver, I'm going to need this field and this field. And you have to tell the name, the units, and everything. And if two processes actually use different units, we drop out. We want everybody to be on board on what a field is. So we need to, what is about to do later.
It will make it clearer. So go ahead.
It's comparable to the register routine.
Yeah. I'm not too familiar with that because I always had bugs in it. So I don't know. I don't want to say too much about it. But yes, initially, essentially you want to define these variables and they have to have grid information with them. Otherwise, how would you tell what extents they have?
So for most of it, we could call it set grids and fields, and then make more sense from the name. So the name is set grids for now, and that's just a simple name. But we are essentially setting the grid that we're running on, but we're also setting all of the variables at this.
Okay, so the fun work starts now. So we did all of this. How many lines? 7 lines in order to just do these 2 calls. One is add field required. So this tells what this call does. It tells the AD, bring me this field to this process. I want to have access to it. And this first one is pseudo density. And I'll explain what the signature are in a second. Let me just find it. Did I misspell something? I'll go back here. Yeah. I think this is better. Hopefully. Okay, good. So what this does, you're asking the, let's just call it EAMxx. You're asking EAMxx. In this process, you're asking EAMxx, I want to have access to this field called pseudo density, and I want it to be required for my process. So if it's not available, everything will crash, but it's required, but I'm not gonna touch it. I'm not gonna update it. I'm not gonna change it. So it's a constant field. So your process is not gonna edit this field. It's gonna read it, but not edit it.
Where does it say the constant field that you're not going to edit?
Required.
So we have a couple of required is an enum value, and there's 2 values, required or computed. Basically input or out.
So required is an input. Computed is
If
not.
you try to write in it and extract a pointer to the data that is non-const, the you get an error at runtime, you can do this, you can't do this check at compile time, but at runtime, it will scrap out saying, sorry, this is read only, you don't have access to write.
And so maybe for reference to everyone familiar with EAM, so in EAM, we would have had PBuff and fizz state, and if you're in dynamics, time state, and fizz 10. So you'd have these separate structures, and depending on the flavor of the variable, it was supposed to be one of those. So that has been removed entirely. We only have the one field manager, and that handles everything. And then, like, so you can think of this as the same way we kind of always did PBuff. Remember when you would add a variable to PBuff, you would do like PBuff add, and then you would kind of give it a name, and then you could later get it from PBuff. It had a similar flavor, but now this is for all variables. But we've also added a layer of protection in that by declaring if it's required, updated, or computed, that sort of enforces a particular behavior by this process on that field. So it doesn't mean pseudodestiny can't be updated elsewhere, but our new process will not be able to change to the next state.
Yeah.
This is a way to protect against accidentally changing a variable with your process that you had no intention to change.
So I'll go ahead and add a tracer, and that will illustrate the keyword updated. So add tracer, and here we're using a different syntax. So we're using add tracer as opposed to add field because we want the tracer we're adding to be advected. So and this one we'll call ash, and it's the signature for this is different, and by design, when you add tracer, it's not like adding fields. And that's by design, because if it's a tracer, it better be on the same grid with the same layout as any 3D variable. We don't want you to choose that. So it has a different signature. So mgrid and then just the unit. And kilogram per kilogram. Internally, kilogram per kilogram will resolve non-dimensional, but it will print kilogram per kilogram if you output the field with netcdf. So that's to add. So I wasn't planning to add this, but since we had the conversation, I'm going to add one more field, and I'm going to call it computed. So if you add a field that's computed, that means it didn't exist before. You're going to make it exist here, and you're going to assign it values. Other processes or I/O can have access to them. And I'm going to call this ash column. And it's going to be the level integrated ash in each column. So I'm just going to call it ash column. But because it is integrated, it is 2D, and it will have kilogram per kilogram. And it depends on how you want to do it, but we can do that. Sure. Is it meter squared or, okay, no, so we need to get the meter then.
Should be like,
so I was actually thinking of doing this as just a sum, like you sum the quantity.
Yeah, well, like if you do total called water is
But that's liquid, like water path.
something like that.
I was thinking of something different, but it is okay to do it. We'll do it this way so that it's similar to liquid water path, like the water path concept.
yeah, I guess it depends on what you do. Like if you make it divide by super density.
For optics, we don't really care about. We want, for optics, what we care about is not the average, but just sum them all. That's what I was thinking about. But we the unit doesn't have to be consistent in the process, but it does have to be consistent if another process tries to call this quantity with a wrong unit, it will fail. But inside you're not going to be penalized for messing up the units later. So it's fine. Rob, you had a question.
You said ash. Ash is a variable that already exists.
No,
Okay, no.
this is going to be adding ash.
Oh, okay.
So to clarify, when it's written as, yeah, so there, we'll get to that later, but updated one implies that it will take the variable that already exists and update it. So it has to have some value before this process runs.
Yep.
Now, it is confusing because no, we know that nowhere else there is a patch, but in one of the next steps, Naser is going
At
to
the very end, yeah. We'll set it to 0 at the very end.
train the initialization.
Yeah, because space, yeah.
I wonder if it would help to actually back up in a second and explain the order in which EAMxx initializes.
You want to do it?
So this is what EAMxx does when it initializes. First, it creates all the grids. So dynamics and physics. Then it creates the processes, but only calls the constructor. So there's nothing around. There's still no fields around. And then it passes the grids that it just created to the processes so that the processors are able to say, oh, okay, so these are the layouts and the grids we have. I need this field on this, I need this field on this. So once all the processes are done saying which field they will need either as input or output or input-output, then the driver's like, okay, now I know every single field that we need, I'll allocate all of them. So that's why this phase, saying that the field already existed is kind of like misleading. No field exists until every process is done saying there's an itemized list of what they need. So once every process is done this phase, then the driver will have the list of every single field that is needed in this run and will allocate it.
So somewhere in the process, someone has to add pseudo density as a field they want.
Yes. So so for example, if you just
Not
has
necessarily.
well, pseudo density has to exist, and so it has to be initialized.
So if a field is required by every process, but nobody computes it, then EAMxx says, okay, it's an input to the atmosphere as a whole, in a way. So if you look at the atmosphere as a single box, then there's an input, so I must be able to find it in the initial condition. So nobody computes it. You can also have a process that computes it and updates the dynamic does that. Dynamic
That's what
updates the pseudo density. But if nobody computes a field before you, like in the sequence of the atmosphere, then the driver says, okay, nobody's computed this field before you in the sequence of the processes once you line them up. So I must find this field in the input file. Or in the initial conditions section, you can set it to a fixed constant everywhere, which we do sometimes for some traits that are initialized at 0. That's also about it. Another thing I want to say, like, okay, updated is just a shortcut to not write the same line twice, once for required and once for computed. It's just to save a line. And then add tracer is also a shortcut to add field with certain inputs predefined, like the layout is predefined. And not just that, but when you call add field, you can actually tell the driver, add this field to a group called block. So maybe later I want to output this group as a whole, or maybe some other process needs to handle this group as a whole. For instance, dynamics handle tracers as a single big entity. So add tracer is just a shortcut to tell the driver not only declare this field, but also add it to the tracer.
Okay, so this will conclude set grids. Any more questions before we move on to more stuff? Yes, go ahead.
Updated tracer. So it will be updated by what kind of process it is?
You will see this. So we update this in the run step, which we will write in a second. So for now, we're just declaring that we're gonna update it, but we don't do anything to it yet. So and set one important caveat is that set grids and initialize impl happen only once at the very start of the run, but don't happen again. Right? So they happen once, and there is one thing that happens during the run at each run step. We'll get to that in a second. Any more questions or comments before we move on to the next fun thing? So this is initialize impl is where we will do the most cocos of all this tutorial. And it's not actually that much, but it is the most cocos. Yes.
Yeah. I mean, for this kind of we don't just it checked these variables. So which time step or how we know the information that here is the information is.
EAMxx will make it available for you at each time step.
Okay, that means so when you execute this process, then what is checked, the lady is not.
Yes, whenever it runs.
So right after set grid is being called for every process, the driver allocates every single thing. And then the next thing that it does that you don't see here, because it's done in the base class, it goes through every process and looks at the list of required and computed that you have. It's like, oh, you require pseudo density? Okay, here it is. I'll give it to you. You require ash writable? Okay, I'll give you a copy of ash that is writable. And then it's stored inside a class. You will not have access to any of the other variables unless you explicitly declare that you have it. And so this process will never be able to access, for instance, horizontal winds, because they never said that it needed it, and the driver will never give the pointer.
And one important detail is, so in the process, in the flow, so it depends on where you put the process, you will get its value. So you might get it before P3 or after P3, but you will define that as a runtime configurable option. And maybe that's what you're asking me.
And it might be a little confusing with all the text, but really down at the very base level, by the time that the process is running step to step, it has access to all the pointers that it said it wants. Pointers to memory. But by declaring the type, that also has, it depends whether or not the pointer will be constant, which is another way of saying like whether or not you can actually change it.
Yep.
So if you try to change a constant variable, then it will throw it in. So if you request that required, then you'll have a pointer, but you'll have a pointer that is also protected against it. So we do this as actually just a layer of protection. It's like because it's available to us in the development step, we make sure this way that no one can inadvertently change data that they had no intention to change. And by doing so, it's similar to when you declare, when you pass a field to the portrait and you declare it as intended, right? You're making sure that it's not going to be misused. So we're doing that on kind of this big driver level.
Yeah, and I think the concept will be clearer once we code the run step part. It will be it will be clear how you actually extract the data and manipulate it. So we'll wait for that. So initialize impl is where we're gonna do the most cocos, and it's a lot of code. So we were gonna calculate a mask. So the idea here is we're injecting a tracer at a certain height with a certain radius, and we thought it would be good to showcase this instead of typing it manually. We will declare a mask that only gets calculated once at the start, and then you multiply your emission rate by this mask to get where you're actually injecting ash. So this step, we will calculate just the mask in the initialize impl.
Before we do, maybe we can first describe what the difference between set grids and initialize impl. So in our case, this is what we're doing for our example, but more generally speaking, what the initial is meant for in the context of your, you can go for this.
No, just go for it.
Okay. So as we said, set grids is really where we're focused on setting the grids and the variables. If there's something that you need to do in your process, whatever it is, just once at the very beginning, that can be allocating certain memory. It can be creating global variables that you intend to use. You don't want to have to calculate the same variable over and over again, which is what we're about to do. Then initialize impl is where you would get. So this will get called once at the very beginning of the run, and then not get called again for the rest of the actual simulation. And so it can be left blank too. There's no reason to calculate it, but it's provided to you, the developer. So we're going to demonstrate one of the use cases.
And you do have access in this. So what you get access to the runtime, but I'm not sure if that's usable at all.
Only useful basically to dynamics, maybe to radiation. Runtime is basically either initial or restart. So dynamics needs to do different things on initial run and restarted runs. So dynamics during initialization needs to know what kind of run it is. I don't remember if RTNGP as well, but the odds are that your parameterization doesn't need to use that.
So
one question about the initialize. You don't actually jump ahead a little bit. You don't initialize the ash tracer, though.
No, that's not what you do.
You don't really need to based on how it's designed, but I mean, like, isn't it always good practice to initialize?
We do it elsewhere. we do it, we initialize the value elsewhere.
By the time initialize impl is called, initial conditions have been set already.
And because it's a tracer, it's part of initial conditions.
Oh, right, because somewhere else you,
Yeah, these are only the methods you have to override, but the driver is doing a bunch of other stuff in between these stuff.
Yeah. So for simplicity, what I think we can do is I can show you the code as written, and then I can copy it later, unless you want me to type all of this
no.
in the front of you and then have.
Just copy and comment it.
Yeah. So I can, maybe what I'll do is copy parts and comment on them very quickly. So yeah, I'll just do that. But the first thing you want to do, if you haven't changed it everywhere, you want to change AP template to POMPEI. So, and then be sure to stay within the curly brackets, because I was about to type stuff outside of that. So the first thing is we're just getting some constants. Again, that's why we wanted to get access to the physics constants. Here we're getting, we're just getting degree to rad. It's just, you know, how you convert that. So pi over 180, and then the radius of Earth. So this should be relatively clear. And the using, so maybe, Luca, do you want to explain what the using is doing?
The using keyword in C++ allows you to give an alias to an existing type. Physics constant is a structure, and it's templating on the type of the scalar stores. If you don't know what templates are, the stuff like okay. And you were just giving a short name so that all the following lines don't contain a long string. That's it. That's all it is.
So when you see using, that's it. We're just saving 30 columns or something. Yeah. Okay, so the next thing we will do is we want to create a field, and this field is the emission mask. So if you remember in the header, we did declare something called emission mask. That was a field, its type was a field. And so what we're doing in this snippet of code, we're allocating that field to 0 to start, but that's all we're doing. This requires a bit of like declaring some stuff, but essentially you declare a name for it, you declare its units, and then you lay out, very similar to how we did the add field computed and required. And then you declare a field identifier for it, and then you just create the field and allocate the view. Allocate the view is the most important part.
So as Naser pointed out, this is actually super great to illustrate. A lot of what you see in that line of all those lines of code are what is happening on the back end behind the scenes by the driver when you're doing this add field. So rather than having to worry about all of that, add field will just, it registers it and then the driver will take care of these lines of code. But in this case, we want to use a field because fields are very powerful variable objects, but we don't want to make it a universal field for everybody. The emission mask is just something the business process cares about. So we're going to make our own local version of the variable.
And we'll be overwriting it. Well, not so because it's initialized impl, it will be set only at one point and never updated again. But you can do the same thing for other fields, and you just override them at each step if you want to share, if you want to save some field or something. But you not that you're supposed to do it. But yeah.
Where is that order company from? Sorry, what's that?
The brand is called EAMxx tutorial material. Mahfouz. Yeah. So after that, we're just going to get, so again, I want to say something about allocative view and deep copy very quickly. So allocative view is very important. You can declare all that stuff and it will be all empty air until you allocate a view. That actually reserves place for it. And then deep copy, you're setting every value in that big array to 0 to start with. Later, we'll be populating some areas with ones or some regions in the array. We're going to get the lat and lon very quickly, and we get these from the grid, the M grid that's already defined. And as This is in degrees, not in radians, so we'll have to convert it. That's why we got that helper function. And by the way, the reason we do auto, as opposed to, in other parts we do not use auto, is because we're telling the compiler to guess the type of this field, but it's a field we haven't declared before, so it's totally new, and it's temporary. It's not gonna be available once we get out of this scope. And then we will look at the target location for just get more information about where we want the injection to happen. So currently, the volcano latitude and longitude are set in the code, but you can change that to make them runtime configurable. In order to do so, you can copy what we're doing for the radius, for the plume radius. And also we're hard coding the emission level to 27, but you can change that to something else. So that's what we're doing here. We're getting more information about things, what we need to do the calculation. Nothing to say about that. Except there's one thing, and it is ECAT require message is a check. So once you're developing code, it would be good to have these checks so that if something goes wrong, you will know exactly where it went wrong and early on. In this case, we know that plume radius cannot be negative, also shouldn't be 0, hopefully. And so if the plume radius is not positive, it will error out and will stop at this line. So it's not should be, it must be positive. And again, remember, plume radius is something you define in the name list. So, and you will see that later. Okay, next we're doing, this is where we start getting into the fun stuff, the cocoa stuff. I mean, it's pretty easy. So what we want to hear, what we want to look at is, so far we didn't really have access to any of the arrays. I mean, we allocated it, but we haven't made it device friendly yet. So what we want to do here is, we want to have these fields, expose them in a way such that we can operate on them both on GPUs and on CPUs. So in order to do that, we extract them as views. And views are essentially just, you can think about them as arrays or matrices. So the first one is we're gonna get the emission view, the mask, the view of the mask, and then we'll get a lat view and a long view.
Explain the stars.
Your stars.
You want me to explain it or you want to explain it?
No, I didn't just kidding.
Okay, so the star, what you will notice first, that the template at the very end of these calls, real, in EAMxx, we define almost everything as real so that we can potentially run it as double precision or single precision. So you can decide that later and elsewhere, and you don't have to hard code anything. So that's what real is for. And then the star is, 1 star means 1D, 2 stars means 2D. So column and level. So in the first one, it is column and level. And in the second one, it is just column. Because the longitude and the latitude doesn't change with level, does it? Maybe it does. I don't know. Yeah. So did I do a good job explaining this, or maybe you want to add something to that? Go ahead.
Here is 1D level, so it's still 1 star.
Yeah, this is
Yeah.
the fact that these are level or column is just for why what these fields are. But this is just say, give me a 1D array, give me a 2D array. And notice that if you pick 2D array, but you declare the field as a layout that is different, it will time say, hey, this doesn't match the layout you declare this field as. You declare this field as having column and levels, but you're passing just 1 star. I can't do a 1D array. It has to be a 2D array. So,
Any question before we go to the lambda?
The star still need pointer?
yes.
It's plus, but not here.
It does mean, it means a pointer.
Oh.
That's the raw data type inside the view is a pointer to real. Or a pointer to real, pointer to real. And notice that if you take away const in one of those two, it will crap out at runtime because you don't have the right to write on lat alone. Those are handled by the Spanish.
So the auto here does return, it's returning a const.
It returns a field. It doesn't, it's not const, but the field's inside has a member that is saying, I am read-only.
Yep. Okay, so now this is kind of maybe the trickiest part, but hopefully it's not so tricky. What we're gonna do, I'll explain what we're gonna do and then we'll do it. What we wanna do is we wanna calculate in parallel this mask that we've been talking about. And again, the mask is now all zeros everywhere, and we're gonna go at every value in it and see if we want it to be 1 or 0. If we wanna update the 0 to 1 or not. And the way we do it, we want to use a parallel policy and then dispatch it. And what we want to dispatch is a lambda. A lambda is just a function that does something to you. And in this case, we want to do it on the GPU. So this is maybe the simplest way I can explain this. But I don't know if Luca wants, what do you want to make it complicated?
Lambda is just a function, period. It's just a function that you can declare on the fly rather than have it coded somewhere else with a return value and blah, blah, blah. The interface of the lambda for a range policy has to be like that. It must take an integer and that's it. The Cocos lambda macro is just some syntactic sugar that Cocos can attach, can add some keyword in front of it if you run on GPU. If you're not running on GPU, it expands to something like a regular lambda if you're familiar with that, C++. And what a range policy is, you don't have to worry about it. It's just for now, just think about it as I run a bunch of for loops iteration in parallel.
And this is very similar to the concept of a lambda in Python, more or less. So if you're familiar with lambdas in Python, it's pretty similar. It's just that we're coding it so that it can be okay on the GPU. And okay, so the way we do it, so there is a function. So lambda is a function that we're declaring here, and we're declaring it as an integer that we call icall. And so once we're inside the lambda, we're looking at the latitude and longitude, and then the change. And if the distance is lower than the plume radius, less than the plume radius, we set the emission mask to 1. That's all we're doing. So we go inside this big grid information, which has lon and lat. And then if we are within a certain radius, we set them to 1, else we don't change them, so they remain 0. And one thing I will mention is note when we discuss the real 1 star, real 1 star, and then real 2 stars, emission view, the emission view we declared above, if you look at it down here, it has in the parentheses, it has 2. It's icall and emission level. And that's also the layout. It's usually column first and then level second. But if you look at the lat rad, lat view and lon view, it has only 1 and it is the column. So that's kind of why we did it that way. 2D versus 1D.
So we're not injecting this plume at a specific level.
We are.
See, the mask is only set to 1 at that emission level.
Yeah.
Oh, I said, I'm at the concept.
It's hard coded.
Yeah. It's right here.
You got a 2D field, but you still have there.
Yeah.
Otherwise, it will be 0. If we're not in that, it will be 0. So this lambda will be parallel on the columns only.
You're using a Euclidean distance formula on a sphere.
Yeah.
This is just
That's
like since I looked up the formula, I was like, this is too ugly. Let's do this. That's not the point here.
Yeah.
Bonus points if you guys want to make it.
So will be the open exercises where you not only add ash to the optical depth, but you also.
But if the radius is small, this is actually, and the grid is like any 30, this probably will work. It's not gonna make a difference using the right.
Oh, I forgot. See, it's unstructured maps, the horizontal direction.
Yes.
Yeah.
And that's, so 2D is.
3D. Yeah. And that's why I really don't like our convention around layout, and then we told them layout 3D.
Well, I had an issue open on GitHub on like renaming the array layout versus the physical, like the geometrical domain dimension. It's a geometrical domain, the rank is 3 because you have horizontal and vertical, but the array has a rank 2. The 2 horizontals are collapsed in 1, but I couldn't find a nice way to make it not confusing, and it was already confusing. I was like, for confusing,
So
I have an idea of how to make it not confusing, distinguishing the array rank versus the rank of the vectorial quantity versus the rank of the geometry where it lives on. It's just
Rob is the our conventions guru. So he'll be in charge of it. Okay, so far we defined this lambda. Note that you close the lambda with a semicolon at the end, and then we're gonna call a policy. I don't think we should spend time explaining what policies are, but if somebody wants to know, we can talk about them. But essentially, very briefly, it tells like the parallel 4, which will be the next line, how to behave. That's all I want to say about it. So it just tells it how to execute this parallelism. If you care about the details, we can get into them in advanced topics later or as an exercise into unwrapping this, but this will get the job done for you. So you give the policy, and we're using this policy. The important part is, or maybe it's not so important, we'll make it device friendly, and it is over columns. That's all. And then once you have that in hand, you can have a parallel 4. The first argument to the parallel 4 is a named, so you name that kernel. So the parallel 4 will be dispatched as what you call a kernel. A kernel is something, a calculation that can happen on the GPU as well as the CPU. So GPUs are only really used for kernel execution. So that's what a kernel is. You can name it. So I'm going to actually call it compute mask. And that will be helpful. Naming these will be helpful for if you're doing profiling or other things. The second argument is the policy that you chose for this. And then the third argument is the lambda that we have just defined it, which is compute mask. And this is the most Cocos will do all day. This is it. Questions?
so this is where the confusion is. Yes.
Yes. They are. All of this is happening at the init time. So there will be more calculations going on later.
But for the mask.
Yes, this is the only time. Yeah.
The values in the mask.
Yeah. This is the only place. And the parallel 4, again, it's what you're doing. You're dispatching something to the GPU to take care of it, and it will return the answers. We're not actually asking it back for the answers, but that's a caveat. Okay, clear? Or should we pause here to talk a little about it, or is everyone happy with where we are?
I said if Cocos has a great online documentation. If some of this looks mysterious, just go on their wiki, just on their GitHub page, or ask.
Seemingly any kind of process, common process, adding this for that was.
If it's only a horizontal direction, yes.
Things, if people want, we can look to unwrap, more advanced like execution, but it really, you will very likely never need that sorts of complexity.
But this is probably more complex.
Sorry?
I'm just executing on its own. This.
What do you mean? Like you have one column or
In the whole model.
Well,
But you want to parallelize over columns as well.
well, yeah, but in EAM, we mostly ignore the parallelism and we just worry about, like for Quebec.
Yeah.
You only worry about stuff.
What's happening in the copy?
What I'm saying is that, is there an equivalent concept? Development processes.
Yeah, I mean, this is kind of, it's essentially.
This is complicated because I have to define this 2D function sphere. Most process models that people develop, only interested in what happens in the vertical. Yes, they want it to happen on every column.
Yes, so
But the
what will happen, you'll have two for loops. Loop over columns that are on my rank and loop over levels. And that's handled in a lot of places in EAMxx, nested parallelism. It's a little more complex, and I really don't want to get into that right here.
Yeah.
But if you're interested, we can show an example.
So this is the innermost part of the loop, this line. So this is,
I don't see it.
but that's so it's hidden.
Parallel forming is
Yeah.
for each integer in their policy range, 0 to n calls, execute that function.
Independent of others.
So the loop is hidden in the parallel form.
Yeah. Well, this is so to your question, Rob, what you can do once you are here, if you are at this line in this implementation, you can do anything you want, and you are restricted to one column and one column only. So you can change emission level to make it, some 3 different levels or do more interesting things.
You can also put a down non-parallel loop inside.
Yes, you can
Yeah.
do a for loop.
It's
It's not going to be good for
Yeah.
performance back and forth.
You don't have to make it efficient, but this is the line where the actual work is happening. So here we kind of showed you, you see a parallel 4 in action. There's a Lambda, there is something dispatching to a kernel and all that. We're going to move on to the run impl where we hide all that from you to just show you that a lot of the basic math that you can think of doing with fields, we already support out of the box, and you don't even have to worry about how the calculation is happening behind the scenes, and it's optimized and works well. And it works well, and it's very well tested as well. So with that being said, let's move to run impl. And the run impl is the part that happens at every time step. So it keeps repeating. So let me go to run impl. We want to change this to, again, if you haven't done it for the whole file, change it to from AP template to POMPEI. And then what we're going to do here is we're going to call the function we defined. So actually, just to make it super clear what we're going to do, we're going to call this function. So we have this function what we defined earlier, and we're going to call it to calculate the emission rate at after a certain time lapse. So after a certain number of days, we just want to call this function, and it will return to us an initial emission with some exponential decay. So this is all we want to do there, and we want to update the tracer with the information we get from here. So let's do that. Let's go back to the run impl. And in the run impl, you have access to the DT as the argument. So you can use that if you want, which we do use it. Okay, so first thing, we will want to know where we are in the time step, because the emission depends on the time where we are in terms of how far we are from the emission start date. So we'll call that timestamp plus DT. And then we will calculate the rate. Again, we'll just call that function that I just opened. And because it is in a different scope, so I'm slightly deviating from what the thing on the left is showing. Instead of using shorthand for POMPEI, I'm gonna write it explicitly, but you can do both just to show you a different way to do it. So ash emission rate, and then we want the input argument to this function call to be days from and where we defined earlier the eruption start. Thanks. Okay, where the the mass, so since it returns a flux, the mass is just the rate multiplied by dt, which is, like your time step.
We're pointing out that dt is not the atmosphere time step, but it's the time step since the last time that this process ran. So if it's subcycle,
It will be
it will
shorter. Yeah.
be divided by numbers. So it's just
Is everything clear so far? We just got a time step. We got where we are in terms of time, and we calculated the rate, how much ash we're injecting. So it's just a simple calculation. We didn't really do anything manipulating the field or put it anywhere, and we calculated the mass. So now this is the fun part where we get access to these fields that we declared earlier. So we want to have the Q ash. Q is for tracer, and then, or quantity ash, and we do get field out ash. So remember ash was added earlier as add tracer updated. So it's an out field. That's how we get access to it here. And then we also want rho, the density, the pseudo density, but this one isn't field out, it's field in, and pseudo density. Hopefully I didn't misspell it again. I don't think so. Somebody will call me. Okay, so now we have access to all fields that we can manipulate. And what we're gonna do is we're gonna manipulate the field without actually doing arithmetics like ourselves. We have these built-in utilities where we can scale field by numbers, scalars, or by other fields. So that's what we're gonna do. The way I would like to do it, just for illustration, before I do that, I do want to access the gravity constant. So I want to get that. I'll maybe declare it here using BC, and we calculated earlier. I don't know where. I never remember any of these things. Here, and then I'm going to get gravity as and then I want to do, I'll just do auto for simplicity, and then PC. I think it's graph, right? Like that.
have two people on your.
Thanks. So what I'm going to do here, we're going to go through a series of field manipulation to avoid doing manual calculations. And the first one would be, we're going to update this field Q ash by, we're going to scale it by 1/G. Actually, maybe it will be clearer if I scale it first by rho. So all I'm doing is I'm multiplying ash by rho. Am I doing this? Yeah. So you have a field and you're multiplying it by rho. And then I'm going to divide by G. So I scale it again by G. And then I update the field. So this just gets me the field as it was saved in the field manager. We did not do any calculations. We did not do any update. We're going to do an update right now.
You didn't do an update with scale.
Yeah, but I meant like in terms of emissions.
Oh.
Yeah. So we haven't changed the emissions yet. We did not account for the emissions yet. So what we're going to do now is we're going to update it using this method called qash.update, and then emission mass by mass, and then 1. So to understand what update does, and it's written oh, I thought I didn't cover it there. But yeah, so when you do y update x a, so x comma a b, it means you're updating y, so y equals b multiplied by y plus a multiplied by x. In this context, it will be q ash multiplied by 1, right? Am I? Yeah, q ash multiplied by 1 plus the emission mass multiplied by the mass. So that is just adding the mass that you calculate the rate to the field, but only where the mass is 1. That's the whole idea. And that's why we did the mass calculation earlier.
So maybe you said, sorry, why can't you do the scale lines?
You cannot.
Because the mass, the other one is mass scalar. It's a kilogram over kilograms.
No, I think he means. I think he means why can't we do the first 2 scale calls in one? Can we? You can't. We can't.
There's a way to do it, but I can show it to you, but it's gonna look a little ugly with
Yeah.
update and some template parameters. You can do a rescale by another field using also an extra scaler. Well, it's possible, but it's just
In general,
for the introductory.
Because I mean, in the second one, you're doing some math and then
so it's one number over another, as opposed to a field. So
Yeah, he's regular, like instead of doing scale 1 over G, you could put 1 over G instead of 1.0 in the second call. That's
we can do that. Well, that's not what he's asking. We can do that, yeah.
but then
But I think it's better
it's different to G is a number, rho is a field.
as a field. And the field really,
Can't be rho divided by 3.
yeah, the rho is a field, and then when you look at the field, you actually don't, there's no data there. I can show you inside the internals how you, when you do these update calls and scale, you actually first have to go inside and access the data. But the field itself doesn't have the data as a pointer to the data. That's how I like to think about it. So what I want to do is actually do the opposite now, to do that, to get out, to get my Q ash to be what it was, by doing, first I will do, it doesn't matter which one goes first. So I'll do rho, and then,
Is the goal of these scale and update functions to never actually have probably tested for next?
but that's what they do actually. It's
I know, but it's,
yeah,
it doesn't look like that.
it's different read, right? Rather than, I mean, it may be more performant to write a single parallel for loop that does all these operations in one, but is that really gonna matter in this parameterization with dynamics that cost so much? No, so let's write.
Well, but I think it's actually more real. Yeah.
It's
A for
real,
loop?
and we could probably with
Well-
some work make it as performant as the single.
So we thought it would be good to showcase that we have a lot of utilities written already, and users can just dip into them without having to do much work.
Yeah, and if then profilers show you that you're spending most of the time here, then sure. go
Yeah,
and
it's, yeah.
Make this,
I'm not there.
but otherwise keep it beat.
Is it clear why, from a scientific perspective, is it clear why I scaled ash by rho divided by G?
I don't see why you scale by 1 over G. It's in rho already. Nice.
Not really. It's the volume, no? That's why, I think. But anyway, that's how we do it for water path. You want to do rho over G, but I actually, we can, this is just a minor, it's just a number. You're scaling by a number, it doesn't matter. So, but this is it. This is run impl. That's how you update the field, the ash tracer in only a very specific location.
You need to add, or you need to add a speaker, add some else.
That's a good point. I forgot about that. So I added let me go back to, and I should implement it on the spot because I didn't try it earlier. So I added a field called ash column, and Shui just reminded me that I was gonna sneak out of this without writing it, so I'll just do it. So what we want to do is if we want to calculate the ash column, we can do that. And we can also do it either manually, or we can do another fancy field method. So I will get to ash column. And then the way I would do it is, after all this scaling, I will need to actually look very quickly how we implemented the vertical contraction, but it should be and then we need some weight. Yeah, I will also look at this. But this is something I added earlier because of the discussion, but then I didn't think it through. So this is the way we're gonna do it. So the first one is actually gonna be Q ash call, and then the second one is the field in, and the third one is a weight. And we don't have a weight, but we can create a weight very quickly.
We send a row and it says.
Yeah, we can. That's actually, no, we want the weight has to be even. So yeah, this column, it's part of the.
Can also be 3D, right? I think you implemented it to people.
Let's look. If we open this function, we try to document the code pretty well. So weight is assumed to be in order of checking either one. So we'll do raw. Yeah, let's just do raw here. So what this call does, I need to include the field utilities, right? And I need to also, if you remind me of that, Luca,
Yeah,
I'll be.
share / field underscore utils.
HTTP. And if this doesn't work, we will know pretty quickly. But this is another fancy little utility we added actually recently, and we haven't really made use of it in the code yet. And it's vertical contraction. And the idea we add all these mathematical tools to the code so that we can use them and simplify the code elsewhere. And in this case, Conrad, you look concerned that I did something wrong.
The comment says the rank 1 field has a level dimension, but it doesn't row, just have one column dimension.
Oh, it also rank 2 with only call and let.
Okay,
Can be either or.
I gotcha.
So, but that's the order it checks. Yeah. So the idea of this, we have this horizontal contraction and we have vertical contraction, and the idea is when you run the code, you can just suffix in the output. You can just say, I want T mid underscore horiz average, and it will actually average T mid over all the globe and return one value in your netcdf file. Now, this might sound pretty silly, but if you are working with super high resolution models, it can be a lifesaver. It was a lifesaver for Peter, who's doing EAMxx development, where instead of outputting these high resolution fields when you're running high resolution EAMxx experiments, you just want one value for the whole domain, and he was using it a lot. So that's kind of why we were inspired to add these. But I'll try to do this as part of the output we're going to get.
So Naser, just kind of restating my question before. So you couldn't put row over G.
No.
But if you wanted to make a field that had row over G,
Yeah.
it's 3D, so you could just pass in there. Is there an easy way to calculate it with these utilities?
You can do this.
Like, so if I wanted to make like a new variable.
You can say row scale 1 over G, and that will make it row over G. But you cannot do.
But yeah, if I wanted to make, because I don't want to change the.
Yeah. So you'll have to create a new field. You can do auto row G.
Yeah, you can clone fields here, but of course you don't want to do it because you're allocating a
It's very expensive.
So what you can do is when you do set grids, you can also say add fields my row or like row scale and compute it. So I want to be able to write it.
This is exactly what you're asking, basically. So you create a row G, you clone it from row, and then you say, but I actually want to scale it by 1 over G. But you do not want to do this at runtime because it will not good.
Can you shortly include again? At the top.
I had to include.
Oh, sorry. Yes. It's share /field /field utils.hpv. I thought you were asking to show the row G again. I was like, why do you need that? And feel free to exclude this. I was planning to make that as an extra exercise, but since Shui asked, we'll do it here. And hopefully it will compile, because who knows? Is this what happens? You're putting me on the spot. But anyway, so now that we've done everything, finalize import, you can add stuff there if you need to clean up stuff from the process. Oftentimes, most likely you don't need to clean up. But if your process is complex, so you have a buffer or a lot of moving parts, this will be a good place to clean them up for closing out. Any examples of what you would do in final import?
You basically need it if you do manual memory management, which you shouldn't. But maybe you're interfacing with an old Fortran library that needs to be cleaned up, then that's the place to do it. But everything that is a field, a shared pointer, or built-in, everything is just automatically cleaned up during destruction, so you don't have to worry about it. But if you're doing manual allocation, then you have to manually deallocate. That's your only chance to do it.
Aaron, how are we doing on time?
Oh, we're at 3 minutes. We're doing great.
Okay, good. So the next thing to do is, this is the fun part of coding the process, but we will need to make it visible, and it's actually quite easy to make it visible. So don't worry. So what we will need to do is we'll need to make a CMake list file in the process, and then we will fill it with information. I actually recommend you just copy this from my code, but if you want, we can walk through it. You don't want to, becoming a CMake expert isn't really, like this is just not, it's kind of outside the scope of development. Like I'm not a CMake expert person, so I have to call Luca and Jim to help us out here. But I would just copy it. The idea here is you list the sources, you define a library, and then you basically link the stuff, and that's really all that's to it. But it is done in CMake language. So I'm just going to copy this into a CMake file in the same, and I'm not going to do anything in finalize import because there's just no need. But you are welcome to write like a little print, and it will print that at the very end of the run.
Okay, Zach.
Yeah, the file name has to be exactly.
Yeah. So let me go back to my code and just copy it because that's easiest. And it's just this file. The other things we'll do by hand, but this one I don't want to do it by hand because we'll be wasting your time if we do it by hand. But yeah, again, the idea is you list the sources so that CMake knows what to compile. You tell it what to compile and what to link, and that's all. Jim, do you want to add anything to that? No, okay, that's good.
The target compile option is
Or
pointless if it's not having any compile option. Like you can delete that.
which one? Target compile option?
Yeah, not having any option.
Yep. Any questions about the CMake?
And also screen utils is not used here, so you can remove it.
What break it?
No, but it's an example of stuff that's not
Yeah. But for the most part, what you will do if you develop a process, you'll just copy one of these files and then edit it so that it's suitable for your process. I would not spend time learning this stuff, to be honest. It's just not going to be. We have experts. You can ask Luca, Jim, they know CMake in and out. That's what I do, at least. I ask them. Okay, so after that, we also want to make the CMake in a directory above aware of our process. And this one will be, so at the very end, so one directory above, you want to just add subdirectory, and you want to do POMPEI. Hopefully I got this right. Okay, good. So that's all CMake. There's not anything else to do with CMake, but there's more stuff to do in terms of coupling. You want to introduce this process to the coupler. And there are two things we need to do. One is to register the physics. So under physics, there's register physics. So if you go to that file, choose somewhere nice, somewhere here, and just add if-def EAMxx as POMPEI, and then say include the header file, which will be physics, POMPEI, and then EAMxx, just the header file of the process, the interface. And then close the if-def. And then once you include, you want to also define it later here by like basically tell the factory to register it. I'm glossing over this because I don't think you want to worry about these details. These are kind of infrastructure details that will be taken care of for you by EAMxx.
It doesn't matter where in that.
No.
I guess I would just one thing to note though, this EAMxx has POMPEI. That's something we have defined in the EAMxx. That's file that we just created. So it's not that when you create a process and you named it capital POMPEI and you insert a process that EAMxx has POMPEI gets automatically populated. That's a CMake flag that we created.
And I believe that this POMPEI here has to be as you defined it in the constructor. Yes. So if you did not like my all capital, all uppercase, make sure that you have it like you defined it. And
explain why we're doing this. When the driver creates the processes, it uses a factory, design model where everything is constructed based on a keyword that is found in the input file, which are those strings. And you have to match the keyword to a function that actually creates it. So it's a factory design, you can Google it. And that's just what we're doing. So that EAMxx knows which function to use to create a process called POMPEI.
Peter, please.
Yeah, two things. One was spelled atmosphere, but the other thing is just to state the obvious thing, just in case people didn't catch it. When Naser said coupler, he didn't mean the component coupler. He means the process coupler within EAMxx.
Yeah, sorry, but yeah.
I can't find it. Where's this? There it is.
It is under physics called register processes.
/ physics.
Yeah.
Why do we need to that?
Easy it is.
It's because if by any chance you don't build that folder, then the type called POMPEI doesn't exist for the compiler in this place. It's just a secret processor trickery.
So there was one little thing left, and I think that's it.
In our case, we're always building POMPEI because that subdirectory was added no matter what. But for instance, man, you could change the CMake configuration of EAMxx to not build man for XX. And at that point, all the source code is never built by the compiler. So we cannot register it here.
Yeah.
The compiler doesn't know what man is.
You can disable, so you can think about this as disabling parts of the code, not building.
Not even building.
Yeah.
Which saves you time on the build.
Yeah.
So if we don't build in for XX, it must be intended.
Go ahead.
Yeah, so when you're registering it, register product, you use the lowercase POMPEI, and I'm confused. I thought we were always using, you'll always use uppercase.
So the uppercase is important at the end. There's uppercase at the very end.
Yeah, but I'm talking about the quoted lowercase POMPEI.
So that's the one that will appear in the XML file. So we'll look
Okay,
at
we
that.
use lowercase.
Yeah, we'll use lowercase there.
Okay.
Like all other processes actually here.
Oh, it's uppercase. So we actually get to choose.
Yeah, sorry.
Well, that's our name. That string is the name we want to, that's the outward facing name we want the users to be using.
Yeah.
Okay.
If they want to use our process. So, nudging is capital N, but everything else is lowercase. Cost is capital C for some reason.
Yeah.
So that's totally up to the developer.
But we're gonna use it in POMPEI. We're gonna make it lowercase. That's why I kept it lowercase. Okay, so the last thing in the MCP coupling layer, you just need to do one little thing, and it's in the CMake file, and it is under, it is above the physics, and there is a folder called MCT coupling. Just find it and you just want to add POMPEI at the very end, it doesn't really matter where you add it, but I would just add after TMS. And in terms of code, really, this is it. We just need to have, we need to do some XML defaults and we're ready. So the XML are at the very, they are right here. So under seam config, I think. So what I would do is find a good spot where like something like TMS or cost or something, or I would just do it before P3 because maybe it's more important than P3. And I'm just gonna copy what I wrote earlier because I don't wanna mess it up. So you can also copy from my XML file. And I did add it before.
Why is that one CMake list file?
That's a good question for, he wrote the MCT coupling layer.
So when we build the ATN lib, we're building a new CMake target called ATN, and we gotta tell CMake that we have a new physics parameterization to make ATN.
I understand why you have to modify the CMake list, but I don't understand that file was directly in CMake. It has nothing to do with that.
Well, it's like this. That's the library that MCT looks for, right? It's the library ATN. It's what MCT looks for, right?
Yeah.
So
That's not even what MCT.
I call it. Yeah, maybe the naming was like unfortunate.
So presumably if we had a Moab, if we couple with Moab,
Yeah,
we would have a
maybe
Moab, we'd have a Moab coupler subdirectory, then we would have the Moab specific files in.
Yeah.
And then we would do, so maybe if MCT coupler and Moab coupler.
You should call it CPL7. That'll make it.
Oh, it's CPL7.
Okay, so just again, just to remind you what you have to do in the XML file, just copy the stuff under POMPEI. This will be the runtime option, the two runtime options we're interested in. And I would encourage you to, just think about what you're adding, read them. And we really like, in EAMxx, we really like people to add a type and doc entries, whatever they add to the code. So if you ever issue a PR, you'll have somebody like me or Luca or others shouting at you to add the little doc string. One very important thing is that came up earlier. This is where we define the initial condition for ash, because we don't have time here to go through and find an initial condition and add ash in it. This is where in the XML defaults, you can set it to 0, and that will make it, when EAMxx runs, it doesn't find it in the IC file, it sets it to 0. Or I don't know if it overrides it if it's written in the IC file, but this is how you set it to 0. And that's why it was add tracer updated, because it is initially set to 0 and it is set right here. Okay, if you are here, we're done. We now are ready to go back to the run script and try to run our code. So the run script is identical to the one you ran with earlier, except these lines here. So it should be identical. Nothing should change. It's the same exact thing. The only thing we're changing here is you're making Scream, that's what we call it now, Scream CMake EAMxx. You're making it run with 11 tracers instead of 10, because we're adding ash as one extra tracer.
When you do that XML change, you have to issue that before you build.
Yeah.
Yeah, I mean, when you issue it, like Seam will tell you, you gotta probably rebuild. Isn't it gonna say that?
I think it works. You have to do it before you run the setup.
No. I mean, you can, but I don't.
No, so if you look at the edit in my run script, I do have the user and L after case setup. You can have it after case setup, it's fine.
Also note that the run script that you guys used from part 1 has all these lines to comment out. So you can just go on comment.
Can I also just go to the
Branch.
case directory I've already built and just
Yeah,
issue those commands, right, to rebuild.
Yes.
yeah, you have to rebuild now.
Yeah, that will be it. So these are the commands. This is the only thing. So the first one is telling Scream to compile with 11 tracers, not 10, because EAMxx now has only 10 tracers. The second one, we're adding POMPEI to the processes that we have. So note how it is plus, because the other ones are default. It will be a good exercise later to move it around if you want in the process list. That's up to you. We're setting these two other calls. They're optional, but you should get used to doing them, I guess. So you're setting the eruption date. You can change that if you want. And then you're also setting the plume radius in K. One more thing I want to show is that now that we have ash, you can actually request it as an output field, 3D variable. But I also requested it here as. Oh, here we go. So look, I requested at model top, model bottom, 400 hectopascal, etc. So you can do that just to experiment. And we also added ash column, so you can request that. So I'm gonna try, what I'm gonna do is I'm gonna copy this run script somewhere, and then I'm gonna try to run with it and see how many mistakes I get. So I'm, talking confidently here, assuming nothing will go wrong, but we'll see. The moment truth is coming. Yeah.
So the column ash is not a new tracer because it's agnostic.
Ash column is not a new tracer, no. Ash itself is a new tracer, yeah. So I'm just gonna, this is the E3SM regular script. I'm just deleting it line by line because I don't know how to do any better. I don't use Vim enough to know how to do things. And I'm glad Luca is not looking. But then I'm just gonna copy my script from that branch and then I will run it and we'll see how many, hopefully we'll get some errors that will be informative. That's kind of part of development, is getting a lot of errors and solving them, and that's how you learn. So don't worry if you get errors. You have people who are been solving these errors quite a bit with you here to help. So this is the script. I want to go to where ash is, and I'm going to add ash column here. Just for the sake of it, and then I'm gonna do, let me also change the case name. I'm just gonna run it, and this should, do I need to change anything else? No. So one thing we're going to do, so if this goes well and people compile, if everything runs, I don't know if it's going to compile, we'll see. We'll try to do some extra exercises. So ways you can make this your own process by adding more things to it, by making it more interactive. But we'll see, we'll get to that in a second. After the tutorial, we're going to move all this content from the tutorial into a web page, so you can browse it and go through it again. And we will also update the run script if Rob allows us. We'll update the run script so that it's super EAMxx friendly, so it can run regular E3SM cases and EAMxx cases with no edits required. So far so good. The external libraries are being compiled, so that's good. Did anyone try to compile yet? Oh. You should go on the problems I created.
Actually, if everybody that got the time to use on that,
Yeah.
things are breaking.
Naser, you all of these changes to the
Yeah. It works. That's the process.
It only works because user analysis call case
After.
I actually wouldn't work if you're just told it before.
Well, since you already create random case up once, the reason is that,
mine's failing.
is it like a fresh build?
So I'm gonna get start again with.
Yeah, so the thing is like ATM change are not copied to the case to the case new folder until case. C has no knowledge.
So did anyone try to compile?
Yeah.
So mine is compiling.
And you're saying like this order.
You know, like, I think he.
Well, no,
Yeah, right here.
so it's there.
Some reason. And then you first got to
This is what we're supposed to see in a bit. If everything goes well, that's what Walter did earlier today.
Every time you run it, it's. Now it finds two nodes in this. Not okay, it doesn't know which one.
Tom?
It's not, that's the issue with using plus.
Is that
Oh, no, just one step. So Walter did it, and we can harass Walter to make more of these.
Oh, yeah, I'm gonna do it up whatever time.
Yes, so that we can, yeah. But you will see it actually go over, like, from Italy and spreading east. Oh, you moved? You put somewhere in Africa? It looks like mine is, so that one thing I will encourage you to do, so I'm gonna open a new terminal window, and I didn't say this earlier, but one thing I would encourage you to do, look at, if you have a good way to look at what is being printed out of the compilation, pay attention to warnings. And one thing you will notice is that these processes, these EAMxx processes, are going to be at the very end.
Naser, I think we might build that. Plus equal to that, so your process. Since build it ML runs more than once, the second time I will try to do it again.
But people should just run it from scratch. Try to do that.
Build an ML runs many times.
Yeah, it runs in the beginning and at the end.
Mine worked earlier.
Okay.
So we'll see.
Well, it depends on. Right, it depends on. It's,
Oh, no, you're right. No, you're right. If you run case setup again manually, then yeah, then.
And so two things you can notice when you, if you look at the E3SM build log to see what's happening, two things you will notice. First, these atmosphere processes will compile at the very end because they require all sorts of things from elsewhere in the code. So they will need, they're kind of the very bottom of the bag. But the other thing you will notice is that it's compiling with NVCC wrapper. So that's how you know you're compiling for GPU. So, and it will run on the GPU, hopefully.
Quick pause so that we can talk about a specific area that some of you might have hit, but some of you might not have gone to yet. But just because we want to give you guys also time to do some fun exercises and stuff afterwards, I just want to quickly run through the air. So as you can see, Naser brought up his build log. So you should hit this air based on everything that we've done so far. This one here, which is kind of not necessarily intuitive. You can see it uses this extended host device. Lambda cannot have private or protected access within its class. This is actually something kind of typical of an error. And we have a few more typical errors that we're going to put on a slide for you in a moment that you will encounter. And we wanted this one in particular because it's not exactly intuitive what the solution is, but it's actually not as difficult as one might imagine either. So we made this, we need to make this one change, and it's not necessarily an error. Go for it. Yeah,
I'll change it, but yeah, keep explaining.
Yeah, it's not an error per se. It's just a nuance of compiling with CUDA. So what we want to do is go back to our POMPEI directory and open the header file for the interface. And so you guys can correct me, by the way, if I get this wrong, but notice that in initialize impl, we created that lambda function that we passed to Cocos. That's the lambda that's being referred to in the error. And that initialize impl is in a protected state in our header file or in our class. And it turns out that I think it's just for CUDA, right?
Yep.
Just for CUDA, we need to actually make it a public member of the class structure, just for CUDA. And so what you're seeing in real time is Naser is putting in this if not defined Cocos enabled CUDA as a way to make sure that for any other architecture that we compile on, we're going to still put the initialized impl into protected state. But for this particular case, because we're actually using CUDA, we need to make sure that it stays in public. So this is actually the simple fix, but it's definitely not something that you would intuit just by looking at the error, right? So you guys should probably all hit this particular error. Yeah. So if you want, you can make that fix. If you're currently building and you don't have this in there, you probably kill the build and know that this fail is going to happen. So you can fix it now.
Did I get it right? That Cocos enabled CUDA like that?
Yeah.
Okay, good.
But you can also just grab that directly from Naser's example. So in his actual example, everything works as you would expect. And so you can just see it there.
So one thing you can do is remove the case scripts directory like this, and then just run again, and it will continue compiling. It will not recompile from the start.
So
it will still go through the motions, but it will be faster compiled.
And there might be a couple of other typos that just be like over that. So I've helped a couple of people where it's totally natural that having gone through all of that code that we added typo. So for sure, be on the lookout for that. But we can help you with it.
So what Walter did, he changed the location of the volcano. So now it's over Hawaii, and you can see how it's spreading.
But yeah, if I made a whole strip, just lined up.
Okay, yeah. So
You need to run the fire. It's higher with the fire right now.
So this is, this is EAMxx with a volcano somewhere across all the Pacific.
Can I just have everyone's attention for a sec? So as you know, you're all working like different levels. You're maybe getting to this point or something else, but essentially the portion of the tutorial where we were talking about how to add stuff and everything like that has come to a conclusion. We are going to hang out. So we're here to help you get past whatever step you're at or help you do something fun and interesting. But I just want to kind of give a formal completion. Thank you all for coming. We want to mention that these tutorial resources will be made available online. We aspire to also put some kind of fun exercises up that you would be able to work on if you wanted to work through them. But give us time, because we're going to be doing that as an aspirational fun thing for our part. But these tutorial, resources will be made available, so you can go back, go through, and work your way through them. We've also come up with a series of fun exercises that we thought you would maybe want to work on if you want to continue to dive a little deeper. So we're going to put those up here. Feel free to take them or leave them. Feel free to move on if you're kind of done with the tutorial. It's been a long day. I totally recognize that, but otherwise, we really appreciate everybody participating. And as I said at the very beginning, this is the first time we've given this. This is kind of the big step where we're bringing EAMxx out and inviting people to get a better understanding of it. So we would really appreciate feedback as well. So if you have feedback for us, you can corner us. We're going to be here all week too. To give us feedback, you can give us formal feedback. But I would hope that this tutorial is something we can give again. And if we can give it better, all the better. So if there's something you thought worked really well, or something maybe we could use improvement on, no feedback will be taken personally, maybe by me, but don't worry. No. But no, please provide feedback. Yeah.
If you want to redirect.
Oh yeah. We'll let Rob set up an anonymous Slack user so that you can to just go to town on us. So feel free to keep hanging out. We're definitely hanging out. And these are just some fun ideas we had if you want to do them.
So one thing is, mega people want our projectors.
Oh,
And so we should probably just look on the slides.
great. Okay, so we're gonna give our projector to the Omega people. But this is the last slide on part 2. So go ahead and just take that up there and, or come up with your own cool ideas. And we're here to help. Thank you, everybody.